Hello there. Today's lesson is about detectors of ionizing radiation. Now, what I want you to do is if I write anything on my whiteboard, I want you to copy this down into your red jotter. I'm going to be showing you some pictures that I've printed out. I just did a bit of Googling for some various detectors. You could either, when you're following this lesson, do a sketch, and you could try and copy a sketch of my photos. If you've got a printer at home and you're able to do this, you could do some Googling yourself and just look for some of these detectors and perhaps print out a picture if you like and stick it in. Excuse me. As long as you've got something, a simple diagram copied from here or Google print cutout. I've got mine printed in color. If you've got a printer and it's black and white, then a black and white print would be just as good. No obligation to do any printing because many of you may not have printers, but if you have, you could add to your notes. So you're going to be copying down what I've got here. You're going to be making some diagrams, possibly doing some printing out and cutting out and sticking in. Obviously, if I was at school, I could give you some of these cutouts for you, but we're not there. And what I want you to do at the end as part of your assignment, and I'll be putting this as a separate assignment with details, is I want you to take some photos of your work that you're doing. Make sure, please, that you get your photos the right way up. No big shadows of arms right across them, well lit, the right way up. It's difficult for me to look at any of your work if it's put in sideways or upside down. And I've had a couple of upside down pieces of work already, and I just have to tell people, look, I can't read that, you'll have to do it again. Okay, so detectors of ionizing radiation. Well, first of all, what is ionizing radiation? We've already looked at alpha, beta, and gamma. And we know that when these particles fly through the air, they can knock off electrons, and then perhaps the air particle, an atom of air, can actually become ionized. And it's these ionized particles that are being detected in a lot of cases. So that's just a little bit of revision from the work you've done already. Now, to start with, the first detector, and this is a bit historical, is photographic film. Now, back in the 1800s, if we go back to a little bit of history, X-rays had been discovered by somebody called Röntgen. And soon knowledge of Röntgen's work spread all around Europe, and other people started building the equipment that Röntgen was using to look at X-rays. And one of the people who started to do work on X-rays following Röntgen's work was a man called Henri Becquerel. So Becquerel had some photographic film. He had some big sheets of photographic film, probably about the same size as an A4 sheet of paper, and he was firing X-rays at them. And then when he got the film developed in some chemicals, this used to be very common, getting films developed. You'd have a camera with a film in it, you'd take pictures, and then you'd take them to somewhere to get them developed. Places like Boots. In Fortrose, you could drop off photographic film in Boots. They would send it away. Somebody would develop the pictures, and you'd get the pictures back in the post a couple of weeks later. So Henri Becquerel was doing all this himself. He was doing experiments with X-rays, with sheets of photographic film, and he found, like Röntgen, he found that the sheets of photographic film that he was developing had patterns or tracks on them which showed that X-rays were present, because you can't see X-rays, you can't taste them, you can't feel them. If you go to hospital and you have an X-ray, you're stood in front of an X-ray machine, and behind you will be some sort of photographic film. Nowadays, they use an electronic version of photographic film, and this is pretty similar to how the camera in your smartphone works. So you get a big smartphone picture, if you like, taken by in your smartphone. There's a little tiny thing called a little chip that records your pictures. In the hospital, you'll have a big sheet of these tiny chips all put together. And again, this can be quite big, as big as this whiteboard here. And instead of developing the film in chemicals, it's processed electronically in the same way that you take a picture with your smartphone. So things have moved on, but photographic film was very useful. Now, what was Henri Becquerel doing? He had some film which he hadn't used. It was blank film, and he had a packet of blank film, and he was going away for the weekend, and he put his packet of film, it's like a 10 pieces of A4 paper in his film, and he put it in a desk, and his desk drawer was a little bit full up, so he put a big paperweight on top of his photographic film to weigh down the paper, to keep the paper weighted down inside the desk. And his paperweight was a piece of rock. Henri Becquerel was a keen walker, and he picked up interesting bits of rock, and he had a nice piece of rock that he picked up, and it was actually granite rock, and he stuck it in his desk drawer, photographic film underneath his bit of granite rock, and he went away for the weekend. He came back after his long weekend holiday, and he was doing some experiments with X-rays. And when he developed his film, he noticed that he had the X-ray tracks on it that he'd seen before, but he also noticed that he had some other tracks which were arranged in a sort of circular pattern. And he noticed that the circular pattern was just about the same shape as the lump of rock. So Becquerel thought that granite rock, actually, he thought that granite rock produced X-rays. But he was wrong. And that wasn't the case, because the X-rays left different traces on his film, and these traces or patterns left on his film were short and thick lines, and he hadn't worked out that granite rock produced X-rays. He was completely wrong, and a bit of lateral thinking, he worked out that there must be some sort of other radiation that was recorded on the film, and it was being produced naturally by granite rock. So what he had in fact discovered was that granite rock wasn't producing X-rays, because the little tracks were a different shape. It was producing tracks of radioactivity. And not X-rays. So now we had a way of detecting radiation by putting a piece of photographic film in the way, and that was used for many years to detect both alpha, beta, and gamma radiation. So that's our first detector. Now, at any stage, you should be able to pause the video. I've had a few pupils telling me that it's quite difficult to pause the Google Meet videos. So what I'm now doing is I'm using Google Meet to record my videos, but then I'm uploading my videos onto YouTube. And YouTube videos use a slightly different system. And I have heard that pupils have said that playing back the YouTube videos of my lesson. In fact, Mr. Garrod was doing this a lot with his fourth years starting from last week, and I was having exactly the same problems. Mr. Garrett said, oh, what you want to do then is record in Google Meet and then upload to YouTube. So you will find that lessons in future will be available on YouTube. And apparently, although I've not tested this, apparently that YouTube videos are better for pausing and rewinding. So at any time, if you need to pause and make notes, I suggest you make notes as we go along. And if I'm getting too far ahead, just pause and make the notes. Okay, so I'm going to rub these out now. Right, now the second detector that I want to talk about is number 2. Second one is something called a cloud chamber. And I'm doing this really because the cloud chamber was invented by a Scotsman called C.T.R. Wilson. Now, C.T.R. Wilson, he was a physicist, and he was also something called a meteorologist. And a meteorologist is somebody who's interested in the weather. Now, back in the late 1800s, there was a weather observatory right on the summit of Ben Nevis, and C.T.R. Wilson, he lived down in the borders where it's fairly flat, but he travelled up to Fort William and he hiked all the way up to the top of Ben Nevis, and there was a huge building which could house quite a number of people who were interested in weather. And every day the meteorologists or the weather watchers would go out and they would record the weather, whether it was sunny, whether it was raining, whether it was snow. If there was snow, how deep was the snow? How visible was it? Were there lots of clouds, or was visibility quite good? And they kept books and books of all these weather records over the years to show what was happening in the top of mountains. And C.T.R. Wilson got really interested in clouds, and he would sit for ages on nice days and watch the clouds come by. Now, because Ben Nevis is quite tall, clouds would come over the top of Ben Nevis, and it would get quite eerie and spooky, and it would get a bit misty and foggy, and then the clouds would go away again. And he also made lots of other observations of things like rainbows and other weather phenomena, things called Brocken spectres, where you can see sort of rainbow outlines of your shadows projected on clouds. And these are quite spectacular if you can get above clouds and have the sun shining down past you onto a layer of cloud, onto what's called a cloud inversion. So C.T.R. Wilson got really interested in clouds, and he went back home to the borders after spending some months on the top of Ben Nevis, and he decided he wanted to try and invent something that would recreate clouds down in the borders. And he worked out how to make something called a cloud chamber, which is a box, a see-through box, like a fish tank. And he worked out how you could make clouds inside his fish tank, miniature clouds. But he also noticed that inside the cloud chamber, and I'll post up a video of this, inside the cloud chamber where he had his clouds, he also noticed that he was seeing these tracks. Now, these weren't just tracks on film, frozen. It was like watching a video, and these tracks would appear out of nowhere, and they would flash across the cloud chamber. And it's a bit like looking up into the sky on a nice clear day and seeing an aeroplane very high up in the atmosphere, and it leads a trail through the sky, and you get cloud trails. And this was just like cloud trails, but inside the box. And he noticed that there were different types of trails, and he soon worked out that there must be different types of radiation, because he was getting short, thick trails. And by now you're probably well aware that the short trails that don't go very far in air are alpha, and he got longer, wispier trails, and he worked out that must be a different type of radiation. And immediately following his work, another scientist called Rutherford decided that he was going to give these trails some names. And the first one that Wilson saw were these short, fat trails, and they were, in fact, alpha particles. And the longer, wispier ones the second type that Wilson noticed, Rutherford called beta particles. Gamma doesn't tend to leave trails in the cloud chamber. So I'll put up a wee video of the cloud chamber in action. You can see these live trails shooting out all over the place. I have in the past built cloud chambers in the classroom. You have to make the cloud chamber very, very cold, and something that we don't have very often, but I have got hold of it in the past, is you need dry ice, which is frozen carbon dioxide down at about -70, and you put dry ice underneath this cloud chamber in a pack, in a layer, and that makes the contents of the cloud chamber really, really cold. And you squirt into the cloud chamber some industrial alcohol, and it vaporizes, just like being at the top of a very cold mountain. You get a vapor inside the box, just like a cloud when it's really cold. And these tracks condense onto the vapor inside the box. So have a look at that video a bit later on. Okay, moving on to our third detector. Now, the third detector I'm going to show you is something called a spark counter. And again, we've got one of these in the physics department, and I would show you it if we were all there, but we're not. So here's a photo of the spark counter, and it's just a little piece of simple electrical equipment, and it's mounted onto a wooden block. And it's it's not much bigger than in the picture, actually. It's about that big. So it's a wooden block, and on top of it there's two electrical sockets, and the red one is a positive electrical socket, and the black one, so I'm going to put positive there, and the black one is a negative socket. And what you do is you connect up a high voltage electricity supply, and you can see this is a diagram of what's going on, and it's about 4,000 volts, and we've got a high voltage electricity supply in the department, and you connect this up to 4,000 volts. On the top here, there's a little sort of window, and the window is covered by what's called a gauze. There's a gauze, G-A-U-Z-E, and a gauze is just a metal grid of wires, of electrically conducting wires, and you hold the radioactive source. And again, we have these radioactive sources in the physics department, locked away in a secure cupboard where people can't get at them. And when you hold your radioactive source above the gauze, little bits of ionizing radiation come shooting out of the source, and they go through the tiny holes in the gauze, and they ionize the air between the gauze and the wire. So I've got a very thin wire, and on top of it I've got the gauze. I'll just draw it from the side, and you get a bit of radiation goes through a hole in the gauze, and it causes the air in the gap between the gauze and the wire, it causes the air to ionize, and we obviously know what that is. And the air is ionized, so an electron is knocked off an air particle, an atom of air, could be anything, could be oxygen, could be nitrogen. It knocks off an electron, and that electron then jumps from the air down to the high voltage wire, and the electron is negative, and it gets pulled down to the positive wire, and as it does so, it makes like a little tiny burst of lightning, a little tiny electrical spark, and the spark's very visible, and it also makes a noise. So you can watch what's going on here, and you'll see these little bursts of sparks and hear them, and they make this sort of clicking noise as they spark across. And that's exactly what lightning is. Lightning's just a burst of electrical activity, burst of electrons, but with lightning, it's obviously on a much, much bigger scale from clouds that are quite high up in the atmosphere, and electrons jump down and make a big spark, and they make the thunder as well. So this is like a miniature lightning generator, and it's called a spark counter. Every time one bit of radiation hits one air particle and causes one bit of ionization, you get one spark. So if your radioactive source is not very active, and by active I mean it's not really doing a lot, it's just producing a little bit of activity, you just get a spark every now and again, and it goes click, click, click. And if the radioactivity is very active, you'll get lots of these, and you get click, 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 and lots of sparks. You see lots of little light sparks, and you hear lots of little crackles as well. So that's detector number 3. It's called the spark counter. Don't forget, pause the video at any time, because I would like you to make some notes. And what do you need? You just need some notes that are similar to what I've got here. If you're not very good at drawing the picture, then perhaps the diagram would help. Or as I said before, get something off Google and print it out. Okay, so that's quite a big thing. Spark counter. Next thing we're going to have a look at, which is based on photographic film, number 4, is something called a film badge. And a film badge is quite small, literally about that big, a couple of centimeters, probably 3 or 4 centimeters square, and it just looks like a badge that you clip onto a jacket or onto your jumper with a safety pin. And I've got a picture here of the film badge. Now there's 2 diagrams here. The one on the left hand side is the film badge. There you can see its pin there for putting on your jumper or your jacket. Now, why would you do that? Well, these film badges are used a lot by people who work in hospitals who are involved with either radioactivity, with stuff called radiotherapy for zapping cancer tumors, or they're worn by radiologists who are taking x-rays to look at broken bones, or x-rays that are used also to treat some types of cancer. And it's important that the people working with radiation, whether it's x-rays or whether it's other types of ionizing radiation like alpha, beta, or gamma, it's important that they don't get zapped by too much radiation, because radiation is quite dangerous. So people in hospitals will wear these, and there are certain laws that say that in a period of time you're not allowed to have more than a certain amount of radiation, and that's spread out over the year. So you'll wear one of these badges, and the badges is a detector of radiation, and every month the badge will be taken away to the medical physics lab, and it will be, the film inside it will be developed, and the technicians will be able to see how much radiation you've had. And if you've had too much radiation in a month, then they'll not allow you to work with radiation again for some period of time. So this is the film badge, and it's shown here as being closed. Well, you can open it up. So this is the closed one, and this is the open one. And again, we've got some of these in the physics department. And you open them up and you put inside a piece of photographic film, which is obviously about 3 or 4 centimeters in size, and you put that inside and you shut up the film badge and you wear it. Now, if you look closely, what you'll see here is that the film badge is made of blue plastic and it's got a window in it. And remember, alpha is stopped by a thin piece of paper. So this is a window that will let alpha radiation in. And when the alpha radiation comes in through the window, it will hit the piece of photographic film and it will leave a trace on it or a track on it, just as we saw earlier. But if you also look carefully, you'll see that there are different types of metal in here as well. And this is a thin piece of aluminium foil. This is just really like tin foil that you use in the kitchen, but it's not actually tin, it really is aluminium. And here's a thicker piece of aluminium, and here's a piece of lead. So if the radiation can get through the open window, then it must be alpha. But if it gets stopped by these bits of metal, then that will tell you it's alpha. It gets through the thin aluminium, it must be beta. And if it gets stopped by this bit of aluminium, then it's definitely beta. And if it gets through the window and the thin bits of aluminium, it must be gamma. But if it gets stopped by the lead, you can definitely see that it's gamma. And the last thing you want, you don't want really, is you don't want to see tracks underneath the 2 bits of lead, because that means the radiation is going to be quite penetrating. And quite penetrating means that if it can get through lead, it can get through your skin and it can get into your body. And radiation getting into your body is a bit dangerous. So this is a film badge. And it's used for detecting X-rays and alpha and beta and gamma with these different layers of metal. So the film badge. So you'll need to get a diagram, and perhaps your diagram will be, if you're not going to print out a picture, you can have the film badge opened up, and you can have an empty window through which alpha will get through, and then you can draw in some different types of metal, and you could label them thin aluminium. I'm going to use the chemical abbreviation for aluminium. I've got thin aluminium, I've got thicker aluminium, and then the one in the middle was lead. And if you know the abbreviation in chemistry for lead, it's Pb. And inside goes a piece of film. Now, the piece of film wasn't in the diagram there, because if it was, it would cover everything up. So the bit of film has been taken out. So you'll need to have something about how it works. You already know about alpha, beta, and gamma and what they can pass through or what they're stopped by. And you should have some notes about how the film badge works based on what I've been talking about. Okay, that's the film badge. Moving on, number 5. And number 5 is the Geiger-Muller tube. Now, Geiger was a university student of Rutherford, and Geiger was using bits of photographic film and the cloud chamber, and he wanted something a little bit better than that. So he invented, along with Muller, he invented something called the Geiger-Muller tube, sometimes abbreviated to GM tube. And the Geiger-Muller tube is connected with a cable to a detector meter. So here is a picture of a Geiger-Muller tube connected with a cable to a detector meter, a counter, and the counter's got a little dial on it, and the dial will move across. The needle on the dial will move across. If it's not detecting any radiation, then the needle will stay at the left-hand side, and if it's detecting lots of radiation, the needle will go across to the right-hand side. And you can see here there's a bit of a color bit. I'll hold it up a bit closer, and you can see it's got a colored bit, and the colored bit would be like a danger zone for radiation. And you can also turn on a clicker as well, so you get a sound as well. And if there's no clicks, you're quite safe. And if you get click, 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 then you know your Geiger-Muller tube and the counter are detecting lots of radiation, and that's probably not very safe. So how does it work? Well, here I've got my radioactive source. Don't know whether you can see the wording on here, but that's the source, and it's a tube. It's a hollow tube, but it's capped at both ends, and the tube contains some gas. And again, it's a bit like the spark counter. Running down the center of the tube is a high voltage wire, and the radiation goes through a very thin window at the end and ionizes the gas inside. And when the ionized gas is detected by the charged up electrical wire, it sends a signal down to the rate meter, and it makes a click. It's a bit like a more modern version where you can actually have a counter on the screen. So what do you need to get written down for that? You need something like this, which is the tube with a wire. It's got a window. I've got some radioactivity here, which is my source. It's got a thin window. It's very thin, this window, otherwise alpha particles wouldn't be able to get in. It's got some gas inside, and it's got a high voltage wire. And what happens? The gas is ionized, and the ionized gas is detected. Can't spell voltage. The ionized gas is detected by the high voltage wire, which sends a signal to the meter, and the meter clicks or shows you how much radiation there is with a needle. So these are some of the detectors, and again, we've got a Geiger-Muller tube and detector meter in the department, which we would normally get out with our radioactive sources, and we'd show you how it all works. But obviously that's not happening at the moment due to lockdown. So those are your detectors of ionizing radiation that I need you to make notes about, diagrams, printouts if you're able to do it. Go on to Google if you want to see some more diagrams that you don't need necessarily to print out, but you'll be able to get some stuff from Google. I'm also providing a link to BBC Bitesize, and BBC Bitesize has got lots of little lessons in it, and there's a video, and I'm going to put a link to the video where you can actually see the Geiger-Muller tube being used, and you can hear it clicking away as the source is held up. And what happens when you put different materials in the gap? What happens when you put paper in the way, or aluminium, or lead? So this is just using a detector to show you some of the information that we have been doing in our previous lesson. Right, I'm going to stop this video just now, and that's it. I'll be stopping it.